The first thing they ask us about is critical values. That's something that's really important to be able to determine. And it says Z alpha over 2. Well, we want to do an 84% confidence interval. So what would be the critical values that would go along with that? So if I've got an 84% confidence interval, that means we've got 0.84 right here in the middle. Outside of that, we've got how much? Okay, 0.08 in each tail. So on my calculator, if I'm looking for a Z value, I would do inverse norm 0.08. So we get okay. Yep, negative 1.40 would be the correct answer for that to get critical values. Well, yeah, negative 1.41. Okay. Do I have to type it in to go to the next one? Okay. Well, you gotta give it the answer. All right. Now what? I don't see enter. Oh, hit enter. Okay. There we go. Next question. Okay. Well, that's going to send the whole thing in. Yeah. Okay. All right. We got Z alpha over 2. And here it says this one corresponds to alpha equals 0.08. So again, if alpha is 0.08, critical value, we're looking for the Z value that has half of alpha in the tail, right? That's what this notation says. We're looking for a Z value such that it has half of alpha to the left. So half of alpha would be 0.04. And so we would do inverse norm 0.04. And I got negative 1.75. Okay. All right. Express the confidence interval 0.55 to 0.99 in the form p hat plus or minus e. Okay. So this is really good because you need to understand from here what this tells us about, what the confidence interval tells us about the point estimate and also the margin of error. So the point estimate is always going to be at the very center of our interval. So if I wanted to figure out what p hat was from this, what I would do is say 0.555 plus 0.999 and divide that by 2. Okay, if we do that, okay, 0.777. That just seemed too easy to do in my head, but okay, 0.777. So that's p hat. And then the margin of error is going to be, remember we said the width of the confidence interval is 2 times the margin of error. So the width is 0.999 minus 0.555. Okay, and I just said this is equal to 2 times the margin of error. So 2e equals 0.444, or e equals 0.222. Okay, questions about how we're able to look at a confidence interval and determine what the point estimate is or what the margin of error is. Okay, very good. Alrighty. Here it says use the sample data and confidence level given below to complete parts A through D. Okay, a research institute poll asked respondents if they felt vulnerable to identity theft. In the poll, N equals 1037, X equals 547, who said yes. Use a 90% confidence level. Okay, the first thing they want us to do is to find the best point estimate for the population proportion P. Well, the best point estimate is going to be what? P hat, which is equal to X divided by N. So 547 over 1037. Okay. Identify the value of the margin of error. What I would do at that point is get out my calculator and start punching in my numbers. We're going to go to Stat, Test. We are doing a 1 proportion Z interval. Okay, choice A. They told us that X was 547. Okay, N is 1037. And the level of confidence is 90%. Okay, and so there's my interval. To get the margin of error, we just said we do what? Okay. Point. All right, so we get basically the margin of error is going to be E equals point, what was the number? 55298. 50198 all over 2. Okay, and so when we do that, we get what? Okay, 0.0255. All right, so that gives me the margin of error. We already found the confidence interval. Okay, from our confidence interval was from 0.5098 to 0.55298. Okay, then it says write a statement that correctly interprets the confidence interval. Choose the correct answer below. One has 90% confidence that the interval from the lower bound to the upper bound actually does contain the true value of the population proportion. One has 90% confidence that the sample proportion is equal to the population proportion. There's a 90% chance that the true value of the population proportion will fall between the lower bound and upper bound. 90% of the sample proportions will fall between lower bound and upper bound. Which one of these is the correct interpretation? Okay, all right, so we've eliminated B and D. B just really doesn't make sense. D, 90% of the sample proportions will fall between. That's not what we're saying. Okay, C says there's a 90% chance that the true value will fall between the lower bound and upper bound. Okay, why is that not the right answer? Okay, the true population proportion is a real number. Okay, and we don't know what that number is, but it is a real number. And once we say this is our confidence interval, it's either in that interval or it's not. So probabilities of that would either be 0 or 1. There's not a 90% chance that it will be in there. So A is the correct interpretation. One has 90% confidence that the interval from the lower bound to the upper bound actually does contain the true value of the population proportion. Okay? Or a better interpretation, I think, is 90% of the intervals constructed in this manner will contain the population proportion, and 10% will not. Okay, questions about that? All right, very good. Okay, yeah. All right. A clinical trial tests a method designed to increase the probability of conceiving a girl. In the study, 410 babies were born, and 328 of them were girls. Wow. Use the sample data to construct a 99% confidence interval estimate of the percentage of girls born. Based on the result, does the method appear to be effective? Okay. The level of confidence is 99%. So we're going to go to stat, test. We're doing a proportion test. All right, X in this case was 328. N is 410. And our level of confidence, we just said, is 99%. So we get 0.749 to 0.851. Okay. Does the method appear to be effective? Yes or no? P hat's at the very center of the interval. It always will be at the very center. Okay. Is this method effective if you're trying to have a girl? No? What do you think the percentage of girls would be, of conceiving girls is normally? 50%. Under this method, we're estimating that the percentage is between 75 and 85%. So do you think it's an effective method? Yes. Okay, it does appear to be effective. Okay, questions about that? All right, very good. Okay, so let's see. A couple of things. I like this one too. It says among the 559 human resource professionals who were surveyed, how many of them said that body piercings and tattoos were big grooming red flags? Okay, and there's some other stuff up there. In a poll of 559 human resource professionals, 49% said body piercings and tattoos were red flags. So how would we figure out exactly how many said that? 559. Okay, 0.49 times 559. Let's see if I can blow this up a little. Okay, 274. Okay, good. All right, construct the 99% confidence interval estimate of all human resource professionals. I think we know how to do that, but let's do it anyway. If we do the 99% confidence interval, okay, we're going to go to stat, test, choice A. X was, it was what? Okay. I'll just do it right here. All right, and then N. Oh, oops. What did you all get? Oh, you called it 274. Okay. What did you get?
I got the integral was 0.4357 to 5.54416.
What did you get when you did 49% of 559?
What you got?
Okay, it was a decimal, but you rounded it up. Gotcha. Okay. N is 559, and the level of confidence is 99%. Okay, we're going to calculate. So we get 0.4357 to 0.54462. Okay. Point 4357 to 0.54462. Okay, then we're going to do this again, except this time we want to do it for 80%. So actually, stat test alpha A. Okay, change it to 0.8. Calculate. And so we get 0.46306 to 0.51726. Okay? And so in part D, it says compare the confidence intervals from B and C and identify where's the thing? Identify the interval that is wider. Why is it wider? So which one of the intervals was wider? The 99% confidence interval. It was wider. Why is it wider? Well, the wider the interval, the more certain we are that we're capturing P. Okay? So that's what I wanted to, I thought that was a good exercise to focus on that. As the level of confidence goes up, then so does our margin of error. Our interval gets wider. Okay? As our level of confidence goes down, the margin of error decreases. Okay, very good. Yes. Okay, use the given data to find the minimum sample size. That's something else that you want to make sure that you know how to do. The formula for minimum sample size for proportions was N equals N equals, who remembers the formula? I think it's Z alpha over 2 over E squared P hat Q hat. Okay? So in this problem, the margin of error is 0.07. And we're doing 95% confidence. Proportion tests and intervals are always Z test. So 95% confidence corresponds to 1.96. We're going to square that. And then here it says P hat and Q hat are unknown. So we estimate them to be what? Well, each of them is 0.5. And when you multiply that together, you get the 0.25. Okay? And so do that on the calculator. And, of course, you're always going to round up to the nearest integer. And what'd you get? You should get more than 1.96. 196? Okay, 196. Okay, questions about that? Minimum sample size. Okay. Good. Okay, that's the one we just did. Same thing here. Many states are carefully considering steps that would help them collect sales taxes on items purchased through the internet. How many randomly selected sales transactions must be surveyed to determine the percentage that transpired over the internet. Assume that we want to be 99% confident that the sample percentage is within 5 percentage points of the true population percentage for all sales transactions. So that's the same kind of problem. We got to determine the minimum sample size, and in this case we would let p hat and q hat be what? 0.5, because they don't tell us anything about it. Okay? All right, margin of error, 9 percentage points. What are we asked to do? Use the given data to find the minimum sample size. This time, they do give us an estimate for p hat. So if we wanted to do that one, the formula is still n equals z alpha over 2 over e squared p hat q hat. Okay, if we're doing 90% confidence, that's what? What's the z value? Okay, I believe it's 1.645. E is 0.09. Okay, 9 percentage points, so 0.09. P hat is 0.32, and Q hat is what? 0.68. Okay, so you multiply all of that together and round up to the next integer. Okay. Questions about that? Okay, very good. Did I skip one? All right, it's basically the same thing again about the sample size. All right. And they give you one where we don't have any previous estimates, and then the second one where they give us an estimate. Okay. A critical value, ZA, denotes the area to the left of Z equals A, area to the right of Z equals A, Z-score with an area of alpha to its right, Z-score with an area of alpha to its left. Which one? Area to the left, okay. Area to the right, okay. It's a Z-score with area of alpha to its left, okay. When we say Z alpha, that's the Z-score with an area of alpha to its left. Okay. Alrighty. Which of the following groups has terms that can be used interchangeably with the others? Critical value, percentage, and proportion. Percentage, probability, and proportion. Critical value, probability, and proportion. Critical value, percentage, and probability. Which one? Very good. Okay. Percentage, probability, and proportion. All of those things mean the same thing. Okay. Blank, single value used to approximate a population parameter. Ideas before I show you the choices. Okay, there are your choices. A single value used to approximate a population parameter is what? Point estimate. Very good. Point estimate would be right. All right. The correct answer below, the number Z alpha over 2, or it says which of the following is not an observation about critical values. The number Z alpha over 2 is a critical value that is a Z score with the property that it separates an area of alpha over 2 in the right tail of the standard normal distribution. Is that right? We just said it's in the left, right? So A is not right. Okay, the critical value is the area in the right tail region of the standard normal curve. Nope. A critical value is the number on the borderline separating sample statistics that are likely to occur from those that are unlikely to occur. That sounds interesting. Let's see what the last one is. The number z alpha over 2 is a critical value that corresponds to an area of 1 minus alpha over 2 to its left. C or D? D. It's D. Okay? When we talk about z alpha over 2, it's a z value such that we have what? Alpha over 2 in the tail. Or if we said z alpha, it's the z value such that we have alpha in the tail. Okay, does that make sense? Yes, okay, good. No, D is right. It's the number. Okay, it says which one is not. I'm sorry. Let's see. Is a critical value that is a z-score with the property that's yeah, A would be wrong. You're right. All right. Because the area has to be to the left. Okay. All right. That's just something good for understanding. I won't ask you a question like that on the test exactly, but I do think that's something that you need to know. That's right. When we talk about Z, whatever that subscript alpha is, that should be area to the left of that Z. Okay? All right. Do one of the following as appropriate. Find the critical value, Z alpha over 2, T alpha over 2, or state that neither the normal nor the T distribution applies. Okay? So what these next little questions are focusing on is how do you decide if you're doing a t-test or a z-test for the mean. That's what this is leading up to. Okay? And of course the same criteria for the confidence interval. So what we have is the confidence level is 95%, n is 22, sigma is known, the population appears to be very skewed. Okay? So the first thing we probably would pay attention to is what? That sigma's known, okay? That might make us consider doing a z-test, right? But we have to have one of two things. Either our sample size is greater than 30. Do we have that? No. Since it's not, we really need, in order for us to do the z-test, for the population to be normally distributed. Is it? No. So for this one, we'd say neither normal nor t distribution applies. All right? Questions about that? Because the sample size is less than 30 and the population is not normal. So in addition to knowing sigma, we would either have to have a sample size that's greater than 30 or a population that was normally distributed. Okay? All right, very good. Let's say E is the correct answer there. Okay. All right, next question. Same thing. This time, let's see. We've got 90% confidence. N is equal to 300. Sigma is 13.0. Population appears to be skewed. Okay, what type of test do you think we should do? Well, this is confidence interval. Are we doing ZT or neither? Okay, we'll do Z. Okay, because first of all, we know sigma. All right, and additionally, we've got a large sample size. N is greater than 30. Okay, so we would do Z. So we might think about, well, if we're doing 90% confidence, we already know that number. It should be what? Yeah. Okay, I did it. All right, 1.645. All right. If you didn't know that, then you could do on your calculator inverse norm 0.05, and that should give you the plus and minus 1.645. Okay. All right, questions about that? Inverse norm, 0.05. Because we've got a 90% confidence interval. Right, we got half of alpha in each tail. So 0.9, we'd have 0.05 out here, 0.05 out here. Okay. All right, very good. Okay, what about this one? Confidence level, 95%, n equals 22. Sigma is unknown. Population appears to be normally distributed. T, very good. Okay, so we would do t-test, and then we'd have to either use a table or our calculator to get this actual critical value. We're doing t because sigma's unknown, and even though we have a small sample size, the population is normally distributed. So we can do the t, and then we're going to do, on our calculator, inverse t, 0.025, and our degrees of freedom would be what? 21. Okay, inverse t. Okay, 0.025, 21. Okay, negative 2.08. And then, of course, we'd also get the positive 2.08. It's symmetric.
Can you go over how to find that table?
Okay.
I couldn't figure out how.
All right. On the table, we would come down to 21 degrees of freedom. And then we said we've got a 95% confidence interval. So that means that there's 0.05 left over. And that's distributed in two tails, right? Which is the same thing as saying we have 0.025 in one tail. Does that make sense? So when we come down to 21, we get 2.08. Okay. It's here. Yep, this one. Let's see. Okay, we had 21 degrees of freedom, and then the area in two tails was 0.05, so 2.080. All right, questions about that? The sample size is one less than sample size. I didn't go into a whole bunch of detail about degrees of freedom, but I'm gonna tell you, I usually don't skip that. Somehow I did. But anyway, when we talk about degrees of freedom for the mean, because it varies depending on what you're looking at, it's kind of like we're at the point in this semester where students start asking, what do I need to make on the test to get whatever? Okay, so let's say, student wants to make an 80 in the class or have an 80 test average. The first test they could kind of blow off. The second one they could blow off. The third and fourth they could blow off, assuming that they could get enough points eventually. But if they want to get an 80, they already realize that I've got to have, I just lost my thought. They realize it's dependent on that last test, right? So if we had 5 tests and 4 of them, kind of go wherever, that last one is not free. So we had 4 degrees of freedom. Does that make sense? So for the mean, it's always one less than the sample size. If we were looking at information regarding the standard deviation, it would be 2 less than the sample size. Those last 2 points really kind of determine your spread. All right, so degrees of freedom for the mean is 1 less than the sample size. Okay? Alrighty, use technology and the given confidence level and sample data to find the confidence interval for the population mean. Assume that the population does not exhibit a normal distribution. Okay? So, question is, are we going to do a t interval or a z interval for the mean? Okay, T. Why are we doing a T interval? Okay, we don't know sigma, but they told us the distribution was not normal, so what else do we have to have? Sample size has to be greater than 30. Okay, so we're going to do a T interval, and we do stat, test, must be number 8 is our T interval. Okay, we'll make sure that stats is highlighted. Okay, our sample mean is 2.0. Our standard deviation was 3.8. And our sample size was 41, was it? Okay, confidence level is 99%. Yeah. So it comes up to be what? 0.39501 to 3.605. All right. Okay, so the next question is the confidence interval affected by the fact that the data appear to be from a population that is not normally distributed? It is. I mean, when I saw that, the first thing I was thinking about was what this is, but it's weight loss. So, that seems reasonable. The choices are no because the sample size is large enough, no because the population resembles a normal distribution, yes because the population does not exhibit a normal distribution. That doesn't make sense for the question. Yes because the sample size is not large enough. I think the only one that makes sense is A. Okay, it's not going to be affected because our sample size is large enough. All right, but we'll see what they said. What's that? I skipped it. Yeah. All right, let's see. What else do we have here? What is the best point estimate of the population mean net change in LDL cholesterol after the garlic treatment? What's the best point estimate for the population mean? Best point estimate for the population mean is the sample mean. X bar is the best point estimate. So in this case, that would be what? 3.2. That's our best point estimate. Okay, then they ask us to construct the 90% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. What does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol? What type of interval are we going to do? T interval or Z interval? T, okay? Because the standard deviation describes the sample, right? And our sample size is greater than 30. All right, so I'm not going to go back through and put it in again because hopefully you got that part. Mm-hmm. There were 44 subjects. Mm-hmm. Yep. All right, questions about that? 90%. Well, the standard deviation that we have is from the sample. We don't know sigma. Right. Then if we don't know sigma, we have to consider a t-test. Right. And in order to do either one, we got to either have a population that's normally distributed or or our sample size is greater than 30. Okay. Questions about that?
Exactly what we say to answer that multiple choice question most confidence intervals suggest about the effectiveness of the treatment? Because honestly, I'm not really sure what to say for some interval.
What interval did you get?
Negative 0.9563, no, yeah, negative 0.9563 to 7.356.
Okay, so we're talking about this thing changing the effect that it has on your LDL cholesterol. Zero's in that interval, right? So potentially it could let it go up, it could let it go down. There's no change. All right, so the choices are confidence interval limits contain 0, suggesting that the garlic treatment did not affect the LDL cholesterol levels. That sounds right. Confidence interval limits do not contain 0, suggesting that the garlic treatment did affect. Well, it contains 0. Confidence interval limits do not contain 0. Ignore that one. Confidence interval limits contain 0, suggesting that the garlic treatment did affect the LDL cholesterol levels. No, it's A. Okay, because of that 0. And in fact, I mean, we might say some people went up, some people went down. We don't know. It seems like it's not a sure thing one way or the other. Okay? Mm-hmm. Yes.
What I'm saying is
Yep, confidence intervals. You could do a T confidence interval or a Z confidence interval. Okay. All right. So we talked a lot about proportions and confidence intervals. Let's see what else is in here. Confidence interval estimate for the mean. We've already started talking about the means. I think we got that. So I want to get over to some of the questions. Oh, here's the other one regarding minimum sample size for the mean. Okay, that's a different formula. Okay, for the mean, the formula for minimum sample size is N equals Z alpha over 2 times sigma over E. I think all of this is squared. Okay. So, in order to estimate the mean amount of time computer users spend on the internet each month, how many computer users must be surveyed in order to be 90% confident that your sample mean is within 12 minutes of the population mean? Assume that the standard deviation of the population of monthly time spent on the internet is 217 minutes. Okay? So, if we're doing 90% confidence, we get what? 1.645. Okay, the standard deviation they told us was 217. Is that right? Yep. And then the margin of error is 12. Okay, so do that on your calculator. Square it. If you need to, round up, and that would give it to us. $885. Okay. All right, we can kind of see that. Yeah. All right. 885. Okay. So then it says, what is a major obstacle to getting a good estimate of the population mean? We didn't even really read the problem. In order to estimate the mean amount of time computer users spend on the internet each month, how many users must be surveyed in order to be 90% confident? Okay, what do you think the answer would be? I would say C. Okay, that's really kind of something way back from the beginning of the semester in planning the study. But it would be difficult to precisely measure the amount of time spent on the internet. How? Oh, maybe so. All right. That's right. And divide it by 12. Divide it by 12 and then square it. Okay. 1.645 Okay. Yep. Okay. All right, next one.
Can I ask, so what's the
What percentage? I mean,
percentage
that's a major portion of what the test is about.
I just want them to,
Yeah, I mean,
to practice more on that portion versus the margin of errors and stuff, you know what I'm saying?
yeah, but see, all of that affects the margin of error. When we say, I mean,
Because see, you just did more, two, this was just concerned with the margin of error when I first came in.
mhm.
I just wonder how many people have versus.
I mean, I don't know exactly. I would look at all of it. But you got to be able to find those critical values, and I think most importantly, you need to know when it's a z-test versus when it's a t-test. Okay. All right. Let's see. Find the best point estimate. We know it's the sample mean. Find the 90% confidence interval. Again, with this one, what type of tests would we do? Or what type of interval, Z or T? Z. We know sigma, and our sample size is large, so we would do a Z interval. Okay? All right. I'm going to skip on and talk a little bit about hypothesis testing. Okay. All right, those are more confidence intervals. Okay. It says claim for the given claim, complete parts A and B below. Okay, the mean weight of beauty pageant winners is 122 pounds. A study of 21 randomly selected beauty pageants resulted in a mean winner weight of 119 pounds. Okay, express the original claim in symbolic form. Okay, oops, I can't do that. Okay, so I would say that the claim is about the mean, and they say it is 122 pounds. Okay, the mean weight of beauty pageant winners is 122 pounds. Okay, identify the null and alternative hypotheses. Well, this would be my null hypothesis. And the alternative hypothesis would be, they didn't say anything one way or the other, so I'd go with not equals to 122 pounds. Yes?
Well, it says that doesn't say that study says 119, so would it be that it's less than?
No, it says this is our sample data. This is our witness. So when we do our hypothesis, the null and alternative hypotheses, they'll always have the same values in them. Then we go and generate some sample data to help us either support it or refute it. So make sure in the null and alternative it's always the same value. Okay? All right, so we got to be able to form our hypotheses. Okay, are you sure you want to leave this question? No. Okay, so, oh, right. So mu equals, there we go. All right, and the 122. Okay. All right, same thing here. Can you form a hypothesis? The claim is at least 31% of internet users pay bills online. A recent survey of 346 internet users indicated that 34% paid their bills online. So the claim is what? Is it about mu? It's actually about proportions, right? What proportion pay their bill online? What symbol are we going to use? For the claim? Greater than or equal to. Well, so in that case we would have to use in Triola's book what? Equal to. Okay, that's what I would use. Because in Triola's book, he does all of the null hypotheses as equals to. We never did a greater than or equal to or a less than or equal to. Some books would let you do that. And really, when it comes to writing it in symbols, it really doesn't make a difference because the value that we're going to put in is that n value anyway. Whether we say greater than or equal to 0.31 or equal to, when we do it in the test, it still comes out to be 0.31. So just for clarity, in Triola's book, he did all of his null hypotheses as equals to. And then the alternative could be what? Less than. Okay, less than. That would be the opposite of at least. Okay, so that's what I would do. All right. That's okay. I mean, I don't have to get a grade. Yes, I want to leave it. All right. Okay, test statistic. The claim is that the proportion of peas with yellow pods is equal to 0.25. The sample statistics from one experiment include 580 peas with 138 of them having yellow pods. Find the value of the test statistic. The test statistic is that witness. Okay, we can use our calculator to get that. If we go to stat test, we're doing a one proportion z-test. Okay, the null value would be 0.25. Okay, X is 138. And N is 580. Okay, and it really, when it comes to the test statistic, it really doesn't even matter about the alternative hypothesis. The test statistic is when we would take p hat minus p divided by the square root of p hat q hat over n. Okay, we're just getting the calculator to do all of that for us. And so this is my test statistic, this z value, negative 0.67. Okay, and that's what we would compare to the critical values. All right, questions about that? Because this is about proportions. All right, versus if it's just z-test, just t-test, those are both about means. But the one proportion z-test is for a proportion. All right, so that's the value of the test statistic. All right. Okay, they do the same thing again. The test statistic is, that z value based on the sample data. All right, everybody clear about that? Okay. That's the test statistic. If that's all they're asking us about, then we don't really have to worry about that part. Okay? All right, assume that the significance level is alpha equals 0.05. Use the given information to find the p-value and the critical values. Okay, the test statistic of z equals 1.72 is obtained when testing the claim that p is less than 0.2. Okay, so if our claim is p is less than 0.2, that's the alternative hypothesis. Oh, it's greater than, I'm sorry. Okay, greater than. Okay, the null hypothesis is p is equal to 0.2. Okay, they gave us the test statistic. They've already calculated that for us. Remember, I told you that the p-value is the probability of being as extreme as that. So p-value is equal to the probability of, in this case, Z being greater than 1.72. Okay, that's what a p-value is. And that's what this question is really kind of asking you about. You know, do you understand what a p-value is? And so you could find that on your calculator by doing I'm sorry, not that. We're going to do second distribution. Normal CDF from 1.72 to infinity. And so we get 0.0427. Actually having to find it by hand won't be on the test. Okay? There are a couple of other examples where we'll look at how the calculator gives us the p-value. Okay? What about the critical value? Okay, for this one, what type of test would we have? Left tail, right tail, or two tail? Right tail test. The alternative hypothesis, the symbol in the alternative hypothesis always points towards the rejection region. So it's a right tail test. We've got 0.05 in the right tail, which means we've got 0.95 over here. So to find the critical value, it's that Z value that separates the 95% from the 5%. So inverse norm, 0.95, we get 1.645. That's what we're going to call it. Okay, 1.645 is what is standardly used for this, even though if you went by traditional rounding, well, it would be 1.645. Okay. All right. Questions about that? Go ahead. Well, yes. I mean, if we didn't have $100 calculators, yes. But more importantly, at this point, this is what a p-value means. Okay? It's the probability of being as extreme as the sample evidence that we got. All right? In this case, because it's a right tail test, there's only one critical value. Okay? Because of my alternative hypothesis, the symbol in the alternative hypothesis always points towards the rejection region. So when it's greater than, it'll be a right tail test. If it's less than, it would be a left tail test. Okay? All right, let's see what we got next.
So how you did it?
Okay. Did it change? Okay, slightly different. Same thing again. I think we're still doing that by hand, so I'm not really so interested in that. So we'll keep on going. Okay, is the time critical values are same thing. Let's get to a better problem. All right. Assume a significance level of alpha equals 0.05 and use the given information to complete parts A and B. The original claim is the proportion of male golfers is more than 0.2. The hypothesis test results in a p-value of 0.194. So they already gave us the p-value. State a conclusion about the null hypothesis. What would we say about the null hypothesis? How do we make a decision about a hypothesis test when we're looking at the p-value? I feel like nobody listened to me in this chapter at all. We fail to reject. It's the small p-values that are red flags. Small p-value is a red flag. So in this case, the p-value is 0.194. What that says is there was a 19% chance of us getting the sample evidence that we got under the null hypothesis assumption. That's not unusual, so we stick with the null hypothesis. Does that make sense? Okay. So we are going to fail to reject the null hypothesis because the p-value is greater than alpha. It'd be C. Alpha in this case is 0.05. All right? Without using technical terms, state a final conclusion that addresses the original claim. So we would say that there is sufficient evidence to reject the claim. Which one was the claim? There's more than... That's it. Okay? The claim was that the proportion is more than 0.2. Well, we said we failed to reject the null hypothesis, which is like, we don't really do this, we don't say it too loud, but it's like rejecting the alternative. Okay? The alternative is not the one that's being tested. But anyway, in conclusion, there's sufficient evidence to reject the claim that the proportion of male golfers is more than 0.2. Questions about that? Okay. Well, we failed to reject the null hypothesis, but the claim in this case was the alternative. Mm-hmm. All right. And actually, B is better. Take that back, because we're not testing the alternative. So B would be the better choice. There's not sufficient evidence to support the claim. All right. I can't say this enough. It's the null hypothesis that's being tested, not the alternative. Okay. So we reserve reject and fail to reject for the null hypothesis. All right. Okay. Very good. Okay, here we've got a p-value of 0.07. Alpha is 0.01. State a conclusion about the null hypothesis. We're going to do what? I think I heard fail to reject the null hypothesis because the p-value is greater than alpha. Okay? Alrighty. Okay, we got some pieces. It says a 0.01 significance level is used for a hypothesis test of the claim that when parents use a particular method of gender selection, the proportion of baby girls is different from 0.5. Assume that sample data consists of 45 girls in 100 births. So the sample statistic of 9/20 results in a z-score that is one standard deviation below 0. So they gave you everything already. Identify the null and alternative hypotheses. What would you say? Okay, so which choice? C? D. Okay, D. They say that it's different from 0.5. They don't tell us if it's greater than or less than. We just know it's something different. Okay? What is the value of alpha? 0.01. Very good. Okay, we're testing at the 0.01 significance level. So that is alpha. What is the sampling distribution of the sample statistic? This goes back to T, Z, or chi-square, which we didn't even talk about. That's not going to be on the test. Okay? So, same criteria. We would want to know about the standard deviation. Did they tell us that? Where is it? Well, it says it's a z-score that is one standard deviation below 0. We know that it's a z-test because that's what they just said. It was a normal distribution. Okay, if they're doing z, it has to be a normal distribution. And that's it. Okay, is the test two-tail, left tail, or right tail? Two-tail because of not equals to. What is the value of the test statistic? what in this information is the test statistic? Nope, but you're getting closer. 1. Okay, when we take what we saw in our sample and then convert it to that z-score, that's the test statistic. So they said, so the sample statistic or test statistic results in a z-score that is 1 standard deviation below 0. Okay, so it would be there. What else did they ask us? Okay, what is the p-value? That's where we would calculate the probability of being as extreme as 1. I'm not going to really do that right now. What are the critical values? Okay, if we're doing 0.01 significance, and we just said it's a two-tail test, then we've got 0.005 in each tail. So we would do inverse norm 0.005 to come up with those critical values. All right, we'd have 2 in this case. Okay, plus and minus, whatever. Okay, then what else? What's the last part of it? What is the area of the critical region? What's the area of the critical region? Alpha. Alpha is the area of the critical region, which for us in this problem is 0.01. Okay? We're rejecting 1% of possible values, the most extreme 1%. All right? Questions about that? Yes. Type 1, type 2 error. Okay, the proportion of settled medical malpractice suits is 0.26. Which of the following is a type 1 error? Okay, well, first of all, we kind of need to know what our null hypothesis is, but it sounds like it's that P is equal to 0.26. Okay, so the type 1 error is rejecting the null hypothesis when it's true. So reject the claim that the proportion of settled malpractice suits is 0.26 when the proportion is actually 0.26. That sounds right. Okay, the other one is reject the claim that, nope, B would be right. Okay. Type 2 error is failing to reject the null hypothesis when it's false. So fail to reject the claim that the proportion of settled malpractice suits is 0.26 when the proportion is actually different from 0.26. Okay, that's the type 2 error. Yes, C, thank you. Okay, very good. Questions about that? Okay. All right, which of the following is not true about p-values in hypothesis test? Okay, here's some things maybe that will help you remember what a p-value is and how to interpret it. A says if the p is low, the null must go. Is that true? Yes. Okay, we said small p-values are red flags. They cause us to reject the null hypothesis. If the p is high, the null will fly. That's the one that's wrong. Okay. Questions about that? P-value is an area. Yes, it's the probability or area of being that extreme. The p-value separates the critical region from the values that do not lead to rejection of the null hypothesis. I don't know about that one, but we're going to leave it alone. Okay. That's it's good. Okay. Okay. If P is low, the null must go. If the P is high, the null will fly. It stays. You're right. So this is the one that looks crazy.
Some of the stuff on my math labs, I actually tried to do
Okay, so D. Then that one looked a little crazy. So yes, that's it. Okay, next question. Okay. A certain drug is used to treat asthma. In a clinical trial of the drug, 26 of 263 treated subjects experienced headaches based on data from the manufacturer. The accompanying calculator display shows results from a test of the claim that less than 10% of treated subjects experienced headaches. Use the normal distribution as an approximation to the binomial and assume a 0.01 significance level. Okay, is the test two-tailed, left-tailed, or right-tailed? Okay, left-tailed. First of all, we can tell it from the claim. The claim is that P is less than 0.1. We can also tell it from the display right here. Okay, it said less than. Okay, what is the test statistic? Okay, negative 0.06. Okay, they gave us the test statistic right here in the display. Okay, what is the p-value? Okay, 0.475. This one is the p-value. Okay, and what is the null hypothesis, and what do you conclude about it? So our null hypothesis would still be equals, and what are we going to conclude? Are we going to reject it or fail to reject? Fail to reject. Okay, the p-value is high, so it's good. Alrighty. Okay, let's see. Same kind of thing there. Let's look at least one regarding the mean, and then we'll stop. Okay. Here we already talked about degrees of freedom. DF stands for degrees of freedom. And if the sample size is 20, then degrees of freedom would be what? 19. Okay. All right, let's look at this one. Assume that a simple random sample has been selected from a normally distributed population and test the given claim. Okay. In a manual on how to have a number one song, it is stated that a song must be no longer than 210 seconds. A simple random sample of 40 current hit songs results in a mean length of 233.1 seconds and a standard deviation of 54.54 seconds. Use a 0.05 significance level and the accompanying mini-tab display, okay, I see it, to test the claim that the sample is from a population of songs with a mean greater than 210 seconds. Ooh. Okay. Got to do this really quickly. Okay, the hypothesis would be, we got to vote for B. Okay, the claim is it must be no longer than 210. So that's greater than 210. Should be, can't be D because that has equality. I don't like C because C has equality too. Can't be A. Where is it? Hold on. What is that? Test the claim that the sample is from a population with a mean greater than. So mu is greater than 210. That would be my alternative. And so it's B. Okay? The claim is that it was greater than. Okay? Now it looks like they're doing a t-test. Why are they doing a t-test? Because what? They didn't give us the population standard deviation. Okay? But our sample size apparently is large enough, it's 40. So we would get our test statistic by going to the calculator, going to stat, test. We're doing a t-test since sigma is unknown. Our null value is 210. Our x our sample mean was what, 233? 233.1. Oops, that's a lot. Okay, our sample standard deviation is 54.54. And sample size was, what was it? 40 something? 40, okay. And then our alternative is, we said greater than. That's how I would set that up. If we're doing a traditional method, then we would have to get those critical values like we talked about earlier. If we're doing a p-value method, I can look right here and tell that I'm going to reject the null hypothesis based on the p-value. Okay?